In this lesson, we're going to take a look at chemical equilibrium, which means we're going to investigate reactions that are happening forwards and backwards at the same time, which brings up the idea of reversibility, which may or may not be something you're familiar with. So let's run through a quick example of what I mean by reversibility, and then we'll jump into the chemical things. So reversible just means if something happens in one direction, it can happen in the other direction. So for instance, iodine is a solid at room temperature, but it sublimates at room temperature, which means it's a solid that changes directly into a gas. It skips the liquid phase. It can change from a gas directly back into a solid. That's called deposition. So the opposite of sublimation is deposition, and this can happen at room temperature. But if we had a sample of iodine and we left it sitting out, it would all vaporize, it would all turn to a gas at room temperature, and we'd have iodine vapor. We wouldn't have any iodine solid, because as that vapor mixes with the air, it'll disperse and be carried out, and we don't really have any way of containing it, and so eventually we're just going to run out of our solid iodine. It'll be gone, and we'll have iodine vapor dispersed throughout our air. But if we close that sample of iodine so it can't get away, the iodine vaporizes, but it's stuck, and that's going to increase the pressure in our container. So here's a sample of iodine stuck in this flask, and this is solid iodine down here, and this purple hazy stuff, that's iodine vapor. So this is sublimated, and it's produced iodine vapor. But that increases the pressure in the flask. There's now more gas in there bouncing off the walls of the containers, and that increased pressure actually forces the particles closer together and causes them to form a solid again. So they deposit back on the side of the flask, and you can see it. There's these little specks of solid iodine on the side of the flask. Well, as soon as that happens, as soon as some of it deposits on the side, there's less vapor, which means less pressure, which means now more stuff can vaporize. And so more stuff vaporizes, but that increases the pressure again, and so more stuff deposits. And so we get this continual exchange of solid to vapor and then vapor back to solid. So it's vaporizing as quickly as it's depositing, and so these two things are happening at the same rate in opposite directions. So the vaporization and the deposition, or sublimation I guess, and deposition are happening same rate, and so we get dynamic equilibrium. The total amount of vapor is not changing, the total amount of solid is not changing, but there is solid changing to vapor and vapor changing to solid. Okay? So that's what we mean. That's what we mean when we say dynamic equilibrium. The total amount of stuff isn't changing, but the forward and reverse things are happening at the same rate. Chemical equilibrium happens in much the same way, except instead of the physical change of solid to gas, we have the chemical change of reactant to product. And we generally think of reactions as following that progression. As we start with reactants, we end with products, and so we write this with our reactants over here, and then the arrow points to the right, and we get our products over here. React and product. Reactant and product. But that's not the only way we can write this. So the reaction proceeding to the right is not the only way we can write this. And in fact, most reactions are reversible. The products can change back into reactants, and under the right conditions, they will. And so we actually get the reverse reaction. But we don't really want to say reactants over here and products over here. We just call this the reverse reaction. It proceeds to the left. And so what happens when both of these reactions are happening at the same time? Well, if they're not happening at the same rate, say if this one's happening fast and this one's happening slow, then the net reaction is going to be to the right. We're going to end up getting more product and less reactant. But if they're happening at the same rate, then the amount of reactant and the amount of product is not going to change, and we'll have reached dynamic equilibrium. And when that happens, we write both arrows at the same time. So both the forward and reverse reactions are happening at the same rate. We're now in dynamic equilibrium. And that's what this graph shows. It shows us what happens to the amount of stuff in the reaction as the reaction proceeds. So we start with lots of reactant, the concentration is high, and very little product, concentration is low. This isn't always the case. We could have started with lots of product and a little bit of reactant, and the same thing will happen. We will get equilibrium achieved because the reverse reaction will occur until we reach equilibrium. So this is just one example, but they always don't start like this. Okay? And you'll also notice that the rate is changing, right? We started with lots of reactant, and it changed to product fairly rapidly, and then the rate at which the reactant changed became less and less and less and less. So if we looked at a graph of rate versus time, you'll notice the reaction rate for the reactant starts out high, and we get and the product reaction rate starts out low, which means we're getting reactant produced faster than product, so the overall amount of reactant is going down, which is what this graph shows, but the overall amount of product is going up, which again this graph shows. But as time goes by, the reaction rate slows down, because as we get less reactant, it's harder for it to react. It happens at a slower rate, and so eventually the rate at which reactant changes to product gets slow. It reaches this spot. But as there's more product, its rate increases until the two match right here at their equilibrium. Now this one happens to show equilibrium achieved up here. Sometimes this will be up higher and these two things will meet up here. Sometimes these two curves will meet at a much lower spot. The equilibrium does not mean there's equal amounts of reactant and product. It just means the rate at which reactant and product are being produced is the same for both the forward and reverse reactions. Okay? And we can actually talk about the reaction quotient, or the ratio of product to reactant in a chemical reaction. And this looks like it's going to be scary, but it isn't. There is a little bit of math here. We're not going to get too involved with this, but we will do an example problem. Okay, so equilibrium is achieved when the concentration of product to reactant stops changing. And this is always going to be our ratio. We're always looking at the amount of product to the amount of reactant. Now, how do we measure amounts? Well, usually we use concentration. With gases, you can use pressures. We're not going to get into that. We're just going to look at concentrations. And so concentration, remember, is the amount of solute per amount of solution. We usually measure it in molarity, moles per liter. So we've looked at this before. So remember what molarity means, moles per liter. So let's look at an example of a generic reaction and then figure out how we write the reaction quotient. Okay, so the generic reaction, where M, N, X, and Y are coefficients, that's our mole ratios, right? And A, B, C, and D are our actual chemicals, our elements, our compounds, our ions, our molecules, whatever they are. Okay? We write the coefficient or the quotient ratio by writing QC, okay, the reaction quotient, equal to this thing. Okay, so QC, the reaction quotient, is equal to the concentration of the reactants, or sorry, the products, divided by the concentration of the reactants. These brackets mean concentration of. Okay, so this is the concentration of C raised to its mole ratio power. This is the concentration of D raised to that power. Okay, now sometimes those coefficients are 1, sometimes they're 7. So you just got to look at your balanced chemical equation and plug in the right stuff. And sometimes we'll be measuring concentrations, sometimes we'll be given concentrations, but this is really not that complicated. It just looks scary. We will look at an example problem at the end of this. So the equilibrium constant is the reaction quotient when the reaction has reached equilibrium. So it's at equilibrium when the overall concentration of product to reactant is not changing. And so that's called Kc, because constant. And C is actually for concentration, and K comes up as a constant lots of times in sciences. I'm not sure why K gets to be a constant, but it is. Okay, so the equilibrium constant Kc is the QC when we calculate it at equilibrium. Equilibrium is going to be reached regardless of what we start with. So for a given amount of product, reactant, or mixture of both, no matter what, the reaction will proceed to equilibrium and we'll get to the equilibrium constant, and that equilibrium constant is the same if we did the forward reaction or if we did the reverse reaction or if we did both of them at the same time. So in fact, one of the ways we make sure that our reaction has reached equilibrium is we'll start with the forward reaction and see what we get, and then we'll do the reverse reaction and see what we get, and if we get the same equilibrium coefficient, then we know we're at equilibrium and we're good to go. Now, we actually are going to use these to predict which way, forward or reverse, left or right, a reaction will occur. And so we have to be able to calculate and associate meaning with both the reaction quotient and the equilibrium constant. So remember, reaction quotient, that's how we actually calculate the ratio of product to reactant. And this is the equilibrium constant, which tells us what that ratio will be at equilibrium. And so a ratio, remember, is a fraction, and we have products over reactants. And this fraction is always going to be greater than 0, but it could be less than 1, equal to 1, or greater than 1. And based on that, we can explain what the Kc means. So at equilibrium, Kc equals Qc. which is the amount of product compared, or the concentration of product compared to the concentration of reactants. And so if we look at what it means if Kc is much larger than 1, so if this is big, that means we have a lot of product and not very much reactant, which means the reaction tends to go towards the product side, or it happens forward or to the right. So if it's a very big number, then we get more product than reactant. The forward reaction is favored. But if the Kc value is very, very small, that means that our products are less than our reactants, so we end up with more reactant. That means it doesn't go forward very well, because remember, we go reactant to product. It actually favors the reverse direction. It's going to head that way a little bit better, and so the left arrow is favored, or the reaction generally would proceed to the left until we reach equilibrium if we started with equal amounts, say. So the reverse reaction is favored in a small Kc, the forward reaction is favored for a large Kc. Now we can actually look at the current quotient and determine which way the reaction is going to proceed, or we can say these are the concentrations of things I'm going to put in there, which reaction am I going to get? So we compare Qc to Kc to figure out what's going on. So let's take a look at that. If Qc is less than Kc, the reaction proceeds to the right. Remember, Qc is the ratio of product to reactant, and Kc is this at equilibrium. So if Qc is less than Kc, that means we have less product than reactant, and that means we need more product. And to get more product, we're going to have more reactant change to product, so it's going to favor the forward reaction. Whereas if we have the opposite scenario, where we have Qc greater than Kc, so there's more product than there should be, and that means we need less product, so we need the reaction to go the other way, so we get less product, more reactant, so the left reaction, or the reverse reaction, will be favored in this case. Now, let's look at an example problem, and then we'll be done. Okay, so determine if the following system is at equilibrium. If not, which direction will the system shift in order to reach equilibrium? So we have this reaction. Nitrogen reacts with hydrogen to produce ammonia, NH3. And it's balanced, so everything there is good. So remember, the coefficient, the reaction quotient is given by the concentration of the reactants. So that would be the concentration of NH3, but this gets squared because of this coefficient, over the reactant. So N2 concentration, that's 1, so I don't have to write that, and H2, and this gets cubed. And we are told what the equilibrium coefficient is, and we are told the concentrations of these things. And so let's take a look and sub in our numbers. So I have 0.5 squared divided by 0.15. That should have a bracket around it. And 0.12 cubed. And I get 964. 0.5. Now this is a dimensionless quantity. We don't put any units on our coefficients, or our reaction quotients, or our equilibrium coefficients, but we still assign a meaning to it, right? So this Kc is, the equilibrium happens when this is 17, and we're at 964.5. That means Qc is way, way bigger than Kc, which means we have more product than we should, right? Our product to reactant is too big, so what we expect is we expect more reactant to be produced until this number gets smaller and smaller and smaller and smaller. The reaction actually needs to proceed to the left, so equilibrium is reached when the reaction proceeds left, or the reverse reaction takes place.